Hello everyone. This is a presentation on implementation and parametric analysis of Memristor models, presented in the 4th annual ICNTE conference. An overview of what has been done in this work. First, we will see what Memristors are and very briefly understand how different models have been proposed. Then, we will take a look at different Memristor models which have been implemented and compared to identify their advantages and disadvantages. All the models have been implemented using Verilog A on Cadence Virtuoso, and the window function has been plotted using Desmos, which is a free online graph plotting tool. Memristor is a combination of words from memory registers. It is a component that changes its resistance based on the amount of current that flows through it. This change in resistance is non-volatile, meaning the resistance will remain unchanged even if the component is disconnected from the circuit or power is switched off. Here we see a memristor symbol. The thick black line is used to denote the polarity. The change in the resistance is determined by the amount and direction of the current flowing through the device. Memristor's are an important component whose potential is still being studied. The non-volatility of memristors is especially useful in design of memories. Using suitable logic such as imply logic gate, in-memory computation is possible. This can open doors for a revolution in computing and computing architecture, which is being coined as beyond Neumann architecture and can potentially get rid of the bottleneck problem we find in our current Neumann-based machines. Let's swiftly go through the journey of developments in memristor models. Memristors were first conceptualized by Leon Chua in 1971. At that time, only existence of memristor was proposed and physical model was not given. After almost 4 decades, in 2008, actual memristor was fabricated by HP Labs, proving Leon Chua's proposed concept. Since then, the research on memristors has picked up pace and various design models of memristor have been proposed. These models offer different advantages and disadvantages, which we shall see further in the presentation. These models have been used to design bigger circuits, such as memristor-based multipliers and even adders. In this work, three memristor models have been implemented and compared. These are the linear ion drift model, the Simons-Turner barrier model, and the threshold adaptive memristor, also called the TEAM model. This comparison can help us decide which model to use in different simulation needs. The linear ion drift model is the first model that was proposed by HP Labs in 2008 after they successfully fabricated the memristor for the first time. The concept of this model can be understood with the help of this simple diagram. Here, D is the physical length of the memristor and W represents the doped region width. The doped region has a lower resistance than the undoped region. Depending on the direction of current flowing through the device, this width of the doped region grows or shrinks, changing the overall net resistance of the memristor. Hence, W acts as a state variable, which decides the net resistance of the memristor. This is a very simplistic approach towards the working of memristor. In the voltage current equation, we observe the terms R off and R on. These are resistance values when the doped region width is at 0 and D respectively. This memristor model was excited by a 50 Hz sinusoidal voltage source of amplitude 1 volt. The resultant voltage versus current characteristic curve can be seen below the model diagram. The smooth curves observed in the characteristics indicate the linear dependence of current and voltage. Moreover, we can see that the lobes created by the positive and negative half cycle of the voltage source are identical, hinting at symmetric switching times from low resistance to high resistance and vice versa. Both of these properties of linear dependence and symmetric switching times are absent in a practical memristor. Therefore, this model is useful only in the cases where highly approximated behavior is needed and accuracy can be compromised. One more drawback, which is not so intuitive, is that it is possible that the doped region width W is capable of overshooting the physical dimensions. Therefore, window functions are used. Window functions keep the state variable within the physical bonds. Here we see a window function plot. For a memristor of length 2 nanometer, we observe that the rate of change of state variable reduces to 0 at W is equal to 0 and W is equal to 2 nanometers. This will prevent the state variable from going out of bounds, but it raises another problem, which is if state variable reaches at the border, the rate of change drops down to 0, so there will not be any future changes in the state variable. Thus, we have to take care that W does not reach either of the boundaries. While the linear ion drift model is easy to simulate, it is also highly inaccurate. The Simon's tunnel barrier model was developed after it was observed that linear ion model was not accurate enough. The actual working of Memristor is still being studied. The equation in this model were developed by fabricating the Memristor and deriving appropriate equations through trial and errors. The model is also modified when compared to linear ion drift, which is visible in the model diagram. Unlike the linear ion drift model, the state variable in this model is the undoped region width. We can observe that this model has very complex equations. This is partly due to the tunneling effect that is assumed to take place inside the memristor. When the state variable x reduces, the flowing current is assumed to tunnel through the small high resistance gap, which can be assumed to be a very thin, highly insulating sheet. The resultant voltage versus current plot of this model is shown. We can immediately see that the lobes of positive and negative half cycle are not symmetric, indicating asymmetric switching times. Lack of smoothness of the curve indicates nonlinear current voltage dependence. In the lower left side, we see variation of state variable x with respect to time. The main drawback of this model is the complicated equations, which make it slow to simulate, but this model is the most accurate model developed so far. A need for simplified model was felt as Simon's tunnel barrier model is highly complex. Therefore, the T model was proposed as a substitute for Simon's tunnel barrier model. Here, the properties of Simon tunnel barrier model have been preserved while trading off accuracy. The voltage versus current and state variable characteristics are shown. We can see that the characteristics are similar to Simon tunnel barrier model, while the model equations have been greatly simplified. As a result, T model is extensively used for simulations. The lobes produced in the voltage versus current curve differ from the Simon tunnel barrier model, reflecting the inaccuracy caused due to the approximation of equations. This is a summary of analysis and state variable variation of all three models side by side. We can see that state variable variation of linear ion model varies completely linearly with applied sinusoidal voltage. Subtle differences between the team and Simon tunnel barrier model can be seen, showing that team model is approximation of Simon tunnel barrier model. In the table, flexibility means that the model can be made to behave as another model by changing its constants appropriately. One more advantage of Simon tunnel barrier model is that it does not require a window function. However, linear ion and T model require a window function to operate. Moreover, the Simon's tunnel barrier and T model implement the current threshold phenomena, where the state variable does not change unless the current flowing through the memristor is above a certain threshold. This effect is shown by the state variable characteristics of Team and Simon tunnel barrier model, as the state variable remains constant for certain time, unlike in the case of linear ion drift model. Thus, Simon's tunnel barrier model can be used in the conditions where less number of highly accurate simulations are needed. The T model is more practical for cases where large number of simulations are needed and a little compromise on accuracy can be made. Thank you.